My name is Felix. I work as an application engineer for area engineering, mostly with 3D tolerance analysis, but also with geometric product specifications and finite element analysis.
Right.
So this is a presentation of Cetol Six Sigma. I'm using currently Creo 7, but Cetol works with pretty much any version of Creo.
Okay.
And this is our small assembly for today. It's called Cam Rocker. We have this cam component here, which rotates and then, of course, pushes the rocker here up, which in turn pushes the push rod here. And what we would like to investigate, how far is this going to be pushed upwards? So the distance between this surface and the top one up here.
Right.
And with Cetol Six Sigma, we can work directly with our 3D CAD geometry, and we can reuse assembly constraints as well as 3D PMI. So I'm just going to connect my Cetol application. About the interface, we work with a 3-step approach. So first, I create my assembly constraints and my analysis objective. Then I add my tolerances and dimensions. And lastly, I run the analysis and I have some visualization options. And then here, that's the model tree. So there, all our components relevant for the tolerance chain will show up. And then bottom right-hand corner, that's the advisor. So if there are any problems with our assembly or tolerance analysis, we'll get some messages here. But first of all, I'll add all the components relevant to our tolerance loop. So that's the housing. So as I add components, they will appear here in the Cetol model tree. Then the pin here, as well as the cam. And now you can see these yellow and purple icons. That's our assembly constraints. So how our parts connected to each other. And they get imported from our Cetol models. So if I've defined constraints there, I can reuse them in Cetol Six Sigma. So that saves me some work. But of course, I can also define them manually here. And then this pin, the rocker arm, and lastly, the push rod. So we got several assembly constraints here as well. You can see we have some tolerances. For example, here we have a position tolerance, perpendicularity tolerance, going from the top here of the rod to the outside diameter. That's my primary datum. And as I click on them, you can see them highlighted in Creo. So these were defined prior using the annotation feature in Creo. So if I do that, I can reuse that information as well. And this is a bidirectional link. So for example, currently in Creo, the perpendicularity tolerance has a value of 0.1. And I can change that in Cetol, and I will get that change in Creo as well. So if I, at the end, want to adjust some tolerances, I can do that in Cetol Six Sigma, and then the changes will also be saved in my Creo model. So that's a very quick and easy way to work with 3D annotations. Of course, I can also manually define these tolerances in Cetol, and I'll show that as well as we move on. So next thing that I want to do is define my analysis objective. I said I want to measure the distance between this surface as well as the top of the push rod. So here we can see that little green arrow in the graphics interface. That's my analysis objective. I can rename that. I'll just call it push rod protrusion, and this is the low position. And I can also have some requirements on that. So I want it to be within plus minus 0.5 millimeters. And the nominal value, 10 millimeters, that's calculated from the CAD geometry.
Yeah.
All right. So I've defined my analysis objective. I could run the analysis now. However, for the housing, I don't have any tolerances imported beside the size dimensions for these holes. So I want to add those manually. So I go to tab number 2, second step of the process, adding dimensions and tolerances. I want to add some geometric tolerances for my holes, some position tolerances. For that, I first need to add my primary, secondary, and tertiary datums. So I'll do that. That's going to be my primary datum A. I'm going to call this one datum B. And then I have a small slot down here, which is my datum C. So I have those 3 here. They will appear in my Cetol model tree. I'll just move them to the top. How do they relate to each other? I'll just add, in this case, perpendicularity to datum B, referencing datum A, a tighter tolerance value, so perpendicularity of 0.2. So you can see size tolerance that got imported from my 3D annotations, but you can see this perpendicularity tolerance doesn't have this green rectangle, so that one only exists in Cetol currently.
Yeah.
So I'll add one to datum C as well, this time perpendicularity to A and B. Then I have my 3 holes here, here, and at the top there. So I'll add a position to that one that can be a little bit looser. 0.4 is fine. And this time I have references A, B, and C. And if I wanted, I could add some material modifiers as well, like maximum material condition, for example. All right, then that one. And for the last hole, we have the same tolerance here. Lastly, this top surface. For that one, I'll just add a linear dimension to A. So we have here, it's just 100 millimeters from A to the top surface here, with a symmetric tolerance of plus minus 0.2. Again, I have options to have limits instead, or plus minus one-sided tolerance if I wanted to.
Can I ask you a question, Felix?
Yeah, of course.
Yes. So this 100 dimension, you just added it. I think it's for the purpose of showing that you are able to add dimensions with tolerances to it, because I could believe it is a dimension that you can get right out of the CAD data.
Exactly. So if I've defined a linear dimension with the tolerance there, I could also import that one. Exactly.
And also if there's not,
well.
and also if there's only a dimension without a tolerance. So for example,
exactly. Then
yeah, they understand.
then it will probably appear as this one here. So then it will have no tolerance.
Understand. Yeah.
Exactly. So that's definitely also possible. And we definitely recommend having those tolerances in your model because it speeds up the process by a lot.
Of course. Yeah.
So now I've added all my dimensions and tolerances to my model. You can see here in the second step, the advisor is empty, so there's no more problems. However, if I look at the first step, we have some messages here. And let's have a closer look at those. So in this case, what does it say? It says fastener joint clearance is ignored. And for any message appearing in the advisor, you can just double click and we'll bring up the help system. And you'll get an explanation on the message, why it's a problem and what I should do about it. So in this case, dependent on the tolerances I added for the holes and shaft, Cetol detected that there's possible clearance between the two parts. And of course, if there's clearance, then the parts would not necessarily be centered towards each other, which is kind of the default position here, which we get from Creo. If we have clearance between this pin and the hole in the housing, of course, due to the spring here, which pushes down the push rod, I would also push down the pin to the bottom. So we would instead actually get contact at the bottom of the hole. And I can simulate that in Cetol with my biasing options here. So in this case, I can establish contact to appear at the bottom. So now it uses the clearance to push this pin downwards. The same here. If I would push down here due to the lever effect here, in this case, I would push upwards for this hole. So let's fix that. And that's what's usually happening with your assembly. You will always have some kind of forces acting on the system, be it gravity or some kind of spring forces. So we'll have contact here at the bottom, here at the top. And then lastly, there's also clearance between this pin and this hole. Well, in this case, there's no force pushing it to either side. So I'll choose the floating option, which basically says Cetol should consider all the possible positions of this pin in the hole for the analysis. All right. Now my advisor is empty. I can run the analysis and have a look at the results. The results, and let's see what we get. So here in the graphics, we have this gray and green bar, which is my worst case result. And then also we have this blue distribution, which is my statistical result. And you can see there's quite a bit of difference between them. But let's first look let's see how that would look like in the assembly, since I can visualize that variation. So I can choose worst case and start the animation. And we can see if each and every one of our tolerances is at the very worst possible position, there's quite a bit of movement in the system. However, we have quite a few tolerances in the chain, so that result is highly unlikely. So in this case, we should look at the statistical result instead. And you can see it's quite a bit less movement, so that's more realistic. So I have the option to animate the worst case result as well as the statistical one. And for the statistical one, I can animate a certain capability range or sigma or defects per million units, pretty much whatever you like. All right, but let's get back to our results. So, well, we can see the target here that was 10 millimeters. And then our limits was, our requirements was plus minus 0.5. So they appear down here. Then we have some information on the distribution. We can see the mean is not 10 millimeter, but instead 9.9. So we are a little bit off center. And then we have so-called quality metrics. So dependent on the tolerances and my set requirements, I will get a certain quality of my result. How far this distribution is within the limits. And currently I have a quality of about capability 1, which would translate to about 1,400 defects per million units. So if I would build kind of 1 million of these cam rockers, about 1,400 cases, this distance would be outside of the 9.5 and 10.5 millimeter range. What else do I get? I get sensitivities, which basically say the relationship between each dimension and my result. And high sensitivities are kind of your critical to quality dimensions. Those you want to have a very close look at. So what does that mean? For example, we have the position of this hole, in this case from my primary datum up and down. And this one has a sensitivity of about 1.5 millimeter per millimeter. So for every millimeter this hole moves up or down, it will affect the distance up here by 1.5 millimeter. And of course, that's because of the lever effect we have here. We can also animate that. I've scaled it up a little bit so we see a little bit more in the graphics environment. So when the hole moves up and down, we can see it will affect our distance up here. And this is really useful to helping you understand how your assembly works. For simple assemblies, in most of the cases, it's quite obvious, but if you have a big assembly, it can be a real help to see if you have defined everything correctly and that you get most of your analysis.
Yeah.
And then we also get a contribution list, basically how much each tolerance contributes to the overall variation of your result. For example, here, position of this hole, currently the biggest contribution, more than 40%. Then it's the distance here, that linear dimension, 25%, and so on. You can see we have about 10, 12 contributors, so 10, 12 tolerances in the chain. And of course, with that many, the worst case result is highly unlikely. So we'll look at the statistical one. So now we can see we have a quality of about 1 capability. That's not that good. I would like to reach a target of at least 1.3. That's kind of a standard target in most industries. Of course, in some, you might want to reach a capability of 1.6, for example, in the medical industry.
Yeah.
So, but first, what I want to do is currently we are a bit off center with our distribution here. So I want to pull it back to a mean of 10 millimeters. And of course, to do that, I would probably do some design changes in my Creo environment, but I can also do some experimentation in Cetol to see what kind of changes I really need to do. So I can use the sensitivity list, and here I have a sensitivity which is 1 millimeter per millimeter. So that's an easy one-to-one translation.
Mm-hmm.
So of course, that's the distance of the surface to my primary datum at the bottom. So if I change that, make that distance smaller by 1 millimeter, since this has a negative sensitivity, I should increase my result. So I will go from 100 millimeter to 99.9. And I can immediately see now we are back to our cat nominal. Now the mean is 10 millimeter here. So I can make some changes really quick here in Creo and Cetol to see how they affect my result. And then when I'm happy with those, I can go back to Creo and make the changes to the cat geometry there.
Right. And even though you
can also see,
I wanted to ask, if you made this dimension of 100 yourself, but even if you would have selected it from the CAD model and trying to analyze your how do you call it, your sensitivity, you're not changing the model, you're just you're tweaking the analysis. Is that right?
Exactly.
Yeah,
exactly.
Okay,
I'm not doing any changes to the CAD model. This is only in my Cetol environment.
Good. Yeah.
So now we can see our quality also drastically improved. We are down to about 190 defects per million units. So that's quite a bit better, and not quite the capability I want yet. And in this case, I would kind of start tightening some of the tolerances to increase my quality. And of course, I would start tightening those top contributors because that will have the largest effect on my result. So for example, I have the position tolerance for this hole here. Currently it's set to 0.4. So let's see what happens if I go down to 0.2. Now we have capability of 1.5. So in Cetol, I immediately see the effect what a certain tolerance change has on my result. I don't need to rerun the analysis every time. So it's easy to kind of have a look at different iterations and see what's the best for your kind of use case. So now I'm at capability 1.5, which is quite high. I said my target was 1.3. So now I could actually go and have a look at some of the lower contributors and loosen them up a bit to save production cost.
Yeah.
So example, I maybe can go from 0.4 to 0.6 in this case. See, quality gets a little bit worse, but still an acceptable range. So I can go through the list and tighten and loosen as required until I kind of hit my target quality, in this case 1.3. So this is an easy way to make some adjustments in the quality of your product. All right, now I'm happy with this one. But of course, if you have a big assembly, you will have multiple objectives at once. You won't only have one.
Yeah.
So in this case, I will just import a file where I've defined another one just to see. So this is the low position. We've done that just now. But now I also have something that's called the high position. And that would look like this. So I rotate the cam until I push the rod in its highest possible position. So I can have multiple assembly objectives as well as multiple assembly positions within the same file. So I don't need to make a separate one for each analysis I want to conduct. And of course, I will reuse everything I defined more for my first analysis. So it's a really easy way to analyze multiple positions and multiple objectives at the same time. When I'm done, I can save all the Cetol information directly in my CAD file. So it will be saved in the assembly file, as well as the kind of changes I made to the tolerances. They will be saved within the separate part files. So I have all that information as metadata within the CAD files. But I can also save it as a separate called CXM file if I want to do that. Then when I'm happy, I can also have a look at the analyzer, which is useful if you have a big assembly with multiple objectives and you want to see how they weigh up to each other. So here I can see, in this case, I have percentage of yield. My low position is very good. My high is a little bit worse. I have a list of all my tolerances here. Of course, I can see the contribution of each tolerance, and I can also see the contribution to the mean shift. If you remember, our nominal dimension in the low position was originally, was nominally 10 millimeters, but due to our assembly constraints, it was actually a little bit less, 9.9 millimeters. So here I can see what actually affects that shift. For example, it was the size tolerances within the housing and the shaft. And now it's also the linear dimension on the housing. Why is that? Well, because I changed that afterwards. So you'll get a better understanding what contributes to a mean shift in your assembly. Then I can also have kind of an overview if I want to see how do my contributors weigh up for each objective. So if I want to tighten one of them, one of my tolerances, in this case, I would probably tighten this one because it will improve both of my objectives at the same time. While if I would tighten this tolerance, it will only affect one of my objectives. So if you have many, many objectives, you can see kind of what is the best tolerance to tighten if you only want to tighten a few of them. Yeah. We'll just give you an overview of your whole assembly. And then the same with my sensitivities and critical dimensions. And then at the end, if I'm happy with the changes I made, I can print the automatic report. I can just put in some information here. So that will appear at the beginning. I can choose what I want to include. If you just want to look at the statistical results, or also include worst case, how many sensitivities, contributors, and then at the end, if I'm happy, we can generate, in this case, the HTML file, but we could also do it as a Word document. This will give you an overview, your result, contributing tolerances. And then in this case, we also have worst case sensitivities, and that for every objective. And then at the end, it's just a list of all the tolerances in your tolerance loop. Yeah, so this was kind of a quick overview on Cetol Six Sigma kind of